So, good day. It is Thursday. There is no lab today. We're doing that next week. And hope you've all been doing well. My main goal for today is to continue chapter 12. There's some more stuff about Newton's I keep calling them Newton's laws. That's my mistake, sorry. There's a few things about a few more examples related to the first law of thermodynamics that I want to cover. And depending on how well we get through those, we may start looking at the other two laws more in depth. If there's any questions, concerns, needs, etc., relating to material from yesterday or even past that, please let me know while I'm getting my presentation finished and ready to go. Yep, loaded the wrong file. Pardon me. I am just all over the place this morning. All right. So, if there's no questions at this particular time, we will keep moving along. Brief aside, if at any point you are having difficulty or have questions, please literally tell me. It is kind of part of your obligation as a student in this class. It's part of the class to ask questions. You can email me anything as well, and I just keep saying that as part of my daily spiel in all of my classes, so sorry if I sound like a broken record. So, yesterday, we began looking at the laws of motion. I keep calling them that. I keep saying that by mistake. We looked at the laws of thermodynamics, read over the basic description of each of them, and started going more in depth on them one at a time. We're still looking at a few of the more in-depth details of Newton's first law, because there's actually a few formulas that can tie into it that are worth discussing. Namely, yesterday we looked at this formula here. This is the formula for the change in a machine's internal energy level based on how much heat is added to it and how much work it's able to do. Heat added is energy coming in, and work done is energy going back out. So those are two factors that can affect how much energy a particular device has at any given moment. How much is it being given to do a task, and then how much is it actually using to do that task. And in general, in the real world, you tend to give machines more energy than they actually use as work, because some of that energy always gets left behind and turned into heat due to friction and just stays behind in the system, heating it up until you cool it off and activate some sort of a coolant system. I have gotten a few more short examples into the notes just so that you can have access to them and the math for them. So we'll just look at these very briefly. First, hypothetical question. Say, yesterday we looked at a case where the piston in this hypothetical situation is doing work on its surroundings. Pistons will do that by expanding, exerting a force as they move out some distance. And when the piston does work in that way, it is using up energy and giving it somewhere else. Like the piston driving the wheels of a train gives up its own energy and turns it into kinetic energy inside of the wheels. This specific example is asking about what happens when you do work on the piston by pushing it inwards where it normally would be expanded and extended. So we're taking the piston and manually pushing it back inside. We're doing 500 joules of work by doing that. And at this same time, the piston's coolant system kicks on and removes 750 joules of thermal energy from the piston. The question then would be, what is its change in internal energy? Now, this is not a representative of how things work naturally if left alone. There's sort of mechanisms at play here that are specifically manipulating the energy level of this particular device. Our delta U is equal to Q plus or minus the work done on or by the piston. In this specific case, heat is flowing out of the piston because we are intentionally trying to cool it off. Like most machines have a coolant system where it'll run water or some other liquid coolant through pipes in the machine to take heat away from it, like your car engine, like your refrigerator. The fans inside of your phone and computer work pretty similarly. So in this case, the Q will actually be a negative number. Q represents the heat flow into or out of the object, and if it's flowing out, then it just happens to be negative. The work term this time around will actually be positive because you are doing work on the piston. Something outside of the piston is pushing into it and giving energy back to it. So that means that the work term this time is actually going to be positive. So work is putting energy into the piston, but thermal energy is at the same time being removed. Normally, if we weren't removing thermal energy, doing work into the piston would probably drive the temperature of the piston up. Because if you're doing work on it and compressing it, you're forcing that hot gas into a smaller volume. It's going to increase its pressure. It will probably increase its temperature too. But this coolant system has naturally kicked on to try to mitigate that and remove thermal energy. So in this specific case, the piston's change in total internal energy will actually be negative 250. We did add energy to it by doing work on it, but the coolant system was able to remove more energy than we put into it. Again, this does not represent what processes would do naturally on their own, but this is a possible outcome. It is possible to reduce the internal energy level of a machine through uses like, through applications like intentionally allowing it to cool off. So it is possible to reduce something's energy level. Hold on to that thought. It'll become slightly more important as we start talking about entropy. Second example, similar to the one from yesterday. Let's add 1600 joules of thermal energy to a piston, and that piston will expand to do 300 joules of work. What is its change in internal energy? We add 1600 joules. It performs 300 joules of work, so that means it's giving up 300 of those joules. So that leaves 1300 joules of energy still inside the piston, just warming it up. And with these numbers, we could also calculate the efficiency of this particular piston. Efficiency, and the formula for that is inth equals machine output divided by machine input. This machine is able to do 300 joules worth of work. That's what it's able to accomplish, but it required 1600 joules of energy to be able to do that, which would make this machine about 18.75% efficient. It's able to use this percentage of the energy it's given as work. And frankly, that's about, again, the mechanical efficiency of the human body. Most machines are pretty inefficient because friction is everywhere and you kind of can't avoid it. So, a couple more quick examples for the sake of these notes. This slideshow is currently on Brightspace. You could download it, you can look over it, do your work along with the work that I present. So these examples are in there and updated. that you can have them in your notes. So, that is what we learned and applied from Newton's first... I keep calling them Newton's laws. I'm so sorry. This is what we learned and applied from the first law of thermodynamics yesterday. It's still just a law of conservation of energy, same one we've been using. And I'm realizing that my presenter mode is clipping again. Sorry. All right. So, the first law of thermodynamics reminded us that energy cannot be created or destroyed. You give something energy, it has to still exist. Or you lose energy, it still exists somewhere. We've been applying that to the work that various machines are able to accomplish, primarily using pistons as an example, since it's the sort of textbook situation where you add thermal energy to a gas, it expands to do work. We're going to look at an additional formula that will help us measure how much work a piston is able to do as you heat it up, as the gas inside of it tries to expand. For chapter 12, we've been kind of flashing back to the old work formulas. The stuff from Physics 1500 that involved, doing work, transferring energy, exerting force, and things moving some distance. So we've kind of been digging that formula back up. We're going to be doing the same thing now, but taking that formula and modifying it to more demonstrate, modifying it to match what is happening inside of a piston as the gas inside expands and contracts. So this is additional formulas related to the work that a piston does, or really the work that any gas can do when it's contained. So our old classic formula for work is work equals force times displacement. To do work, you have to exert a force on an object, and that object has to move some distance as a result of the force that you exerted. You're accomplishing some task in that way. And that's true of a piston as well. The gas inside the piston expands, it exerts a force on the actual piston valve, the extending part, and it will push out and extend some distance as it's exerting that force. So this formula does still work for the expansion of a piston. But some very smart people realized that you can calculate force by using pressure, gas pressure, and surface area. The definition of pressure is force divided by surface area, so therefore force would equal pressure times area. In this specific case, this would be like the air pressure, the gas pressure inside of the container, inside the piston valve, inside the piston cylinder. And when a piston is being operated, if you add thermal energy into it to cause the piston to expand, what happens is as you increase the gas's thermal energy level, you're increasing its pressure, and therefore it tries to occupy a bigger volume by pushing out on the walls of its container. And so the pressure exerted over the surface area of the container creates force. The gas exerts more force outwards on all of the walls of the container, and the wall that is the piston itself is the only wall that's designed to move, to slide back and forth with the variable pressure. So that pressure is acting on the surface area of the inside of the canister, and of that canister's surface area, only one of those flat walls, in this case we're presenting the inner side of the piston as just a flat spherical piece of, flat circular piece of metal. The flat surface area of that circle is the only area inside the piston that's designed to move. So when the pressure pushes harder on that specific area, that creates force that pushes that circle and pushes the piston it's attached to further out. So the gas pressure times the area of the valve, the area of the circular flat part of the piston valve, is equal to the force that the gas is exerting on that particular flat circular part. And then once some very smart people made that connection and rewrote the formula to look like this, those same people realized that area times change in length, so this is the flat circular area of this inner part of the piston mechanism, and the delta X represents how far out the piston gets pushed. So the distance that the expanding gas pushes the piston outwards. Area times that change in length would equal the change in volume of the cylinder, because this flat circular area extended over this linear distance, area times distance would be volume. So area times change in distance would be change in volume. So this represents how the volume increase of the entire cylinder. Subsequently, if the cylinder was to contract, it would also be the volume decrease of the cylinder. And so that was then modified again to become pressure times change in volume. Work equals pressure times change in volume. And this is an especially fortuitous way of writing the formula, because we already talk about pressure and volume when it comes to gases and gas law. Those are already variables that we're measuring and want to be aware of when we're working with gases and pneumatic systems. So work equals pressure times volume is just a very convenient formula. If you're able to measure the pressure inside of a system and you know its change in volume as it expands and contracts, then you can calculate the amount of work that that system is either doing on something else if it's expanding, or the amount of work that's being done on it if it is contracting. So this way of writing the formula is very convenient for that reason. It's another way that we can try to calculate the work that a system is doing. And again, it's based on one of the old formulas we already had. It is literally the same formula, just rewritten, kind of. It's the same information presented, just rearranged into different variables. Force was already equal to pressure times area, and delta volume is already equal to area times delta X. So, questions or issues thus far? Concerns, comments, etc.? Okay. So, useful formula. Couple of things to be aware of about it. Work is positive when the gas expands. This would be, if the gas is expanding, delta V would be a positive number, and that's why you would get a positive work out from that. Work is negative when the gas contracts, because you'd have a negative V, therefore you'd have a negative W. If the gas is contracting, work is being done on it. It itself is not doing work. Some small things to note about this particular formula. It's designed to work when volume is changing. If the volume of a system does not change, then technically it's not doing any work, because technically it's not extending to occupy more volume. So there are hypothetical situations where, say, you have a pneumatic cylinder as a part of your system, you heat it up, but it doesn't expand. If you're changing its temperature, but it does not expand, it's not actually doing work in that situation. This formula only works when the volume changes. If volume does not change, then technically there's no work being done. You can change the pressure, change the temperature all you want. If volume doesn't change, no work is being done on or by the piston itself. It's kind of similar to how you can push all you want against a wall. If the wall doesn't move, you're not technically accomplishing any work. In that case, you're just wasting your own energy. There's a few other points here, but I'll bring those up as they become relevant. So, quick example, just to show a brief proof of concept for this particular formula. Let's say we have a valve, a pneumatic cylinder, whose base volume is 1 liter, and the air inside that cylinder is at 1 atmosphere's worth of pressure. 1 atmosphere is the standard pressure unit. That's the amount of air pressure you are currently under on Earth's surface. And we will cause the valve to begin expanding to a larger volume of 1.5 liters. How much work is this piston accomplishing? So, formula, work equals P times delta V. Our pressure is going to be constant, so a constant 1 atmosphere, times our change in volume. Delta anything is always final minus initial, so 1.5 liters minus 1 liters. That tells us that this piston, as it expands in this way, will do 0.5 units of work. So, formula's pretty straightforward. Won't be just a few things to subtract and multiply. There's another caveat to be aware of, though, and it's that you'll have to pay attention to what units you're plugging into the formula, and that will affect which unit you get out of the formula. Liters and atmospheres are valid metric units of volume and pressure. So when you put those into this formula, what the unit out for pressure that you'll get is liters times atmospheres, which is technically a valid metric for work. Like, you could convert that into an amount of joules. It's like the difference between watts and horsepower. You just need to keep in mind that it is a different unit. If you plug in liters and atmospheres, you won't get joules, you'll get liter atmospheres, which is a weird unit. It feels kind of weird to say. It is possible to convert liter atmospheres into joules. I've got the conversion listed down here and on the previous slide. 1 liter atmosphere is equal to 101.325 joules. And so, in summary, if we were to convert our 0.5 liter atmospheres into joules, we'd have 50.7 joules. So that's how much work this particular system does in units of joules. Let me know how this feels. Again, any questions, issues, etc. So, short example, short sample of things to be aware of as you're doing this particular type of question. Next, I'm going to move on to another example, and it's going to be a slightly longer one because it's going to have more parts to it. It's going to be the same formula, just expanding it to a slightly bigger degree. And this next one is specifically either the same as or very similar to one of the Chapter 12 homework questions. So I wanted to make sure to show it and talk about it, to point out some things, some useful information about it before you try to do this one on your own. So, been talking a lot about pneumatic cylinders and how they will expand and contract and do work as thermal energy is added to and taken away from them. Those cylinders are designed to work in cycles, because stage 1 is they expand and do work. Stage 2 is they need to be reset, and then you'll keep looping back and forth between the work stage and the reset stage. You want it to keep pushing whatever it's pushing on, but it needs to be reset first, and then it'll keep doing its work over and over. So this is a cycle, a thermodynamic cycle. Pretty much every piston pneumatic system is designed to work like this. It does its task, it resets, and then it keeps doing it, looping back and forth the whole time. Kind of like the caster on the wheel of the train. Piston expands, drives the wheel forward, piston contracts, pulls the wheel back, and it causes the spinning motion of the train wheels. This cycle, we can break it down into stages. We can try to demonstrate what is happening during each of these stages and figure out how much energy is involved in each of those individual parts. What sort of things are going on in each of those stages. So this particular question, and the homework question similar to it that you'll be doing in the near future, is about each of those different steps of the cycle and what's happening energy-wise in those steps. So this particular question is going to take us through, just the thermodynamic cycle of a 1 liter pneumatic cylinder with gas in it, and we're going to continuously be contracting and retracting this particular cylinder as the pressure changes from part to part. So, our first part, the gas expands from a volume of 1 liter to 3.5 liters at a constant pressure of 6.5 atmospheres. Our formula from the previous slides, again, is work equals pressure times change in volume. So if we want to figure out how much work the cylinder is doing in this particular system, the work done by the gas, then we're going to take our constant pressure of 6.5 atmospheres, multiply it by our change in volume. So we end at 3.5 and we start at 1.0. So 6.5 times about 2.5 gives us a work of 16.25 liter atmospheres. And since WebAssign likes units of joules, it's likely going to ask you to convert that into joules. I've just shown what that value would be equal to. Again, the conversion there is 1 liter atmosphere is 101.35 joules. So, piston expands. It does work on its surroundings. That makes sense. That's consistent with what we've said so far. So, that's that first step. The piston is given energy, it expands, it does its particular task. Now that it's extended, there are steps you have to go through to reset it so that it can then perform that initial task again. So, the first step is that the gas inside needs to be cooled until the pressure falls to 1.5 atmospheres. So, the size of the gas, the volume of the gas and the volume of the expanded cylinder isn't changing in this stage. All we're doing in this particular stage is cooling the piston down as its internal pressure changes. The volume is not changing in this step. Now, our formula can technically handle a change in pressure. Change in pressure is fine. In this particular case, our pressure is falling from 6.5 down to 1.5. So that's a change in pressure of 5 atmospheres, which is a lot. The formula can actually handle that. You're allowed to plug in a difference in pressure. What the formula can't handle is when volume does not change. If volume isn't changing, so we expanded to 3.5 and we're remaining at 3.5 for right now, volume's not changing, so delta V is automatically 0. The formula can take either constant P or delta P, but it must always have delta V. You cannot plug in a constant volume here. It has to be delta V. Because if the volume doesn't change, it's not doing work, nor is work being done on it. Therefore, If the volume's not changing, system is not doing work, so you won't get a positive answer. System is not having work done on it, so you won't get a negative answer. You'll just get an answer of 0. Because if the volume's not changing, delta V is equal to 0. So for this particular step, no mechanical work is being done. There is energy moving around, because in order to cool the cylinder, you do have to remove thermal energy from it, and that'll be done by some outside cooling system. But that system exists outside of this particular cylinder. As far as the cylinder is concerned, it's not doing work right now, nor is work being done on it. The next step, now that the pressure is reduced, the piston is naturally going to want to occupy a smaller volume. There's less pressure inside of it, therefore there's less pressure pushing the gas out to this increased volume. As a result, it's naturally going to contract with that reduced pressure. The gas inside is not exerting as much force. It can't keep the piston extended anymore. So the next step, the gas is compressed at a constant pressure of 1.5 atmospheres from a volume of 3.5 liters down to 1.0 liters. So 1.5 is now our new constant pressure, and our gas is going to 1.0 from 3.5. That's a decrease in volume, so our delta V will be negative. As a result, our work will also be negative. If the piston is contracting, if it's getting shorter, then work is being done on it, not by it. So, in terms of the work being done by it, you'd get a negative answer here. Because from the piston's perspective, if you're solving for work done by the piston, work being done on it would be negative. So that would give us a negative 3.75 liter atmospheres, which would convert to negative 380 joules. So, these two steps here have existed to reset the piston. The last step is this step D here, is the final step needed to fully reset it so that it'll soon be able to actually do its job again. All three of these steps existed so that we could do the first step again. So this last step here, D, we've already got its volume back down to normal. We've contracted it to its original volume. Now we need to get its pressure back to what it was before so that it's ready to extend the piston again. We decrease the pressure to decrease the volume. Now we need to increase the pressure again before the volume will increase again. So, finally the gas is heated until its pressure increases from 1.5 atmospheres to 6.5 atmospheres at a constant volume. So, our pressure is going to change. That's okay. Pressure is going from 6.5 to 6.5 from 1.5. But, like with step B, our volume's not changing this step. So, no work is being done either on or by the system. I will admit I have a small typo here because the constant volume is 1.5 atmospheres and I was still using 3.5 for some reason. The final answer would still be the same because what I wrote here is still a delta V of 0, but I did write 3.5 instead of 1.5, and I'm only realizing that just now, so I apologize for that. So be aware of that. I'm sorry for that mistake. That said, delta V is still 0 here. We're increasing the pressure, probably by heating the gas. We are heating the gas up, increasing the internal pressure, but its volume isn't changing yet, so no work done in or out. Another answer of 0. It'll only do work again once it's allowed to expand again. And so all of these steps exist in a cycle. Extend, then there's 3 steps needed to contract it again, then it's ready to extend again. This is one reason why machines and mechanical engineering can get so fiddly, is it takes a lot of energy for a machine to actually be able to reset itself to do its own job again, depending on its design. So, in terms of energy use, you spend more time maintaining than you spend actually acting. It can be kind of a pain. The last question currently presented here is, what has the network done by the gas on its environment during this complete 4-stage cycle? So, that is going to be our cue to take all 4 of our answers and add them together. This is the lump amount of work that this particular system does in its main acting phase, but at a different phase, work is done back on it. So when you add all these numbers together, you'll get a final answer of 1266.5 joules. Give me just 1 sec. I need to take a quick pause. I'll be right back. All right. Sorry about that. So, any issues, thoughts, needs, concerns, opinions about that, please let me know. I'm hoping that the math involved in this particular process is not too complicated. The formula for the piston expanding and contracting doesn't have a whole lot of terms in it to keep track of, which is kind of nice. And thankfully, neither for this nor delta U equals Q plus minus work are there any new constant tables that we need to worry about. So that's a nice change of pace too. That said, these smaller, straightforward formulas have a tendency to chain together because they're all interconnected, and as we saw here, pistons specifically go through these stages in a cycle constantly. So occasionally you'll have to do, one calculation right after the other with slightly different variables. So that is the most common context that these formulas might come up. And with that, that is the bulk of the first law information that I wanted to discuss. Give me just a sec. Okay, there is one more quick example that I want to briefly look at. For the previous examples using this formula, one, we were using liters and atmospheres. And when you plug liters and atmospheres in, you'll get your final work answer will be in units of liter atmospheres, which is a weird unit, and I don't especially care for it. If, hypothetically, which is what I show here in this example, you were to plug in meters cubed for volume and pascals for pressure, those metric units are specifically designed such that when you multiply them together in this work formula here, you'll get an answer of joules. So, liters times atmospheres creates liter atmospheres. Meters cubed times pascals creates joules. So, the unit you get out from this formula will depend on the units you put into it, and different questions will probably give you different units. It's something that you're going to have to watch out for. So, that is, excuse me. That is all of the Newtons I keep saying Newton. Oh my gosh, this is becoming a problem. That is all of the first law of thermodynamic dedicated information. That doesn't mean we're going to stop talking about Newton's first law, because it's kind of important to every branch of science. So we'll keep referring back to it. But what this means is now we're going to look a little closer into the other 2 laws of thermodynamics. We don't have much longer today if we want to break at 11 as we usually do. So we'll just go over 2 and 3 again with a very cursory glance, and then tomorrow we'll tie everything together and tie it all together, look at a few more examples that utilize pretty much all of the thermodynamic stuff that we've looked at so far. So, oh dear. Well, the formatting on this slide has turned out terrible. I'm so sorry. I can change that real quick. There we go. Oh. Almost. All right. Don't know why that happened. I'm so sorry. Let me check to make sure that you are seeing the fixed version. Okie dokie. So, again, we'll conclude today by looking quickly at the other two laws of thermodynamics. I said it right that time. So, the second law of thermodynamics. This is, I would say, most often brought up or most often referred to as the law of entropy. And I hope that you'd have heard that word prior to this class, depending on what science classes you've had before, or possibly depending on what movies you've seen before. Entropy is a concept. It's important to science. It comes up, therefore, a lot in science fiction. I'd say most famously, it's brought up by Jeff Goldblum's character in the Jurassic Park series, which is suddenly relevant again. His character, Ian Malcolm, is a mathematician, but he also calls himself a chaos statistician or something to that effect. So he specifically studies the math behind entropy. So if you watch that movie and hear what he's talking about, that's basically Newton's... I almost said it again. Basically what he's talking about is this law, the second law of thermodynamics. The law states that the entropy of the universe does not change for reversible processes and increases for spontaneous processes. Now, practically what this means is the entropy level of the entire universe is constantly, slowly rising. And the definition of entropy is basically chaos. If you remember our discussions about what thermal energy is, when objects possess thermal energy, their particles are moving around more randomly. The hotter you make something, but the more its particles move around, the more chaotically its particles move around. And if you'll recall, when I mentioned that every single physical process has some amount of thermal energy created in it, because there's always some amount of friction involved. Therefore, every single time something moves, every time a physical process is performed, some amount of new thermal energy is created, or rather, some amount of existing energy is converted into thermal energy, just by virtue of there being friction and inefficiency in every single action that can hypothetically take place. This means that every time something moves, every time that there is, friction turning more energy into thermal energy, that's slowly increasing the total thermal energy level of the entire universe. And since increases in thermal energy correlate directly to increases in chaotic movement, therefore contributing directly to the increase in entropy, every single action in the universe increases the total entropy level of the universe. And again, if you've watched Jurassic Park at all, that's what Steve Goldblum's character is constantly talking about. There's chaos in every situation. Entropy levels are constantly rising due to every single new unique action. Now, thermally speaking, in terms of what this means for thermodynamics, is one, all machines, every single physical process has some degree of inefficiency, which tells you how much of the energy involved isn't used for work that sort of ends up turned into thermal energy. And two, it means that the entropy level of a given object will slowly increase as it starts doing work as, there's friction involved in its processes, and more of its own energy gets turned into thermal energy. Now, there is hypothetically a way for something to not increase the entropy level of itself or the universe, and it would be if the machine, the process, was completely 100% ideal. Ideal being, what I mean by ideal is if there's no friction involved, if the machine or the organism is 100% efficient in how it operates. If, say, a machine was able to take 100% of the energy it was given and use it for 100% of that value in work, then that would be an ideal reversible process. There's no irreversible energy transformation. There's no irreversible damage caused to some object that couldn't be repaired. You have the energy still present. It's not turned into thermal energy. Friction didn't try to slow things down, break things down, slowly ruin everything. That is the only hypothetical action that would not increase the entropy of the universe as a whole. But ideal 100% efficient actions in machines are completely hypothetical. We don't have any actions that are completely ideal because there's always friction. There's always some complication. No process in the universe is truly 100% mathematically reversible because there was always energy loss and energy transformation in that process. If you could create 100% efficient processes, then there would be no net increase of entropy in that situation. But since all real spontaneous processes are mathematically irreversible because there's some amount of energy transformation, because friction always takes some of the work and turns it into thermal energy, all real actions that we are able to observe in the universe increase entropy slowly. It turns more energy into thermal energy, and all that thermal energy does is make the entire universe as a whole warmer. So that's the second law of thermodynamics. It comes up a lot in multiple disciplines of study, and on the whole, it's kind of depressing. The third law of thermodynamics kind of exists to balance the second law back out. The second law says that for every action, the total entropy of the universe increases, because for every action, the total thermal energy level of the universe slowly increases, since friction always is involved in every process, and since friction is always making more. What the third law tells us, third law of thermodynamics, says that the entropy of a system approaches a constant value as its temperature approaches absolute zero. I'm going to elaborate on that because that's the official physics version. But what it means is that you can increase an object's entropy level, its chaos level, by increasing its temperature. This makes sense. You increase temperature, you increase thermal energy, its particles will move around more randomly. You can therefore reduce the entropy level of a specific object or of a specific system by removing thermal energy from it. It is possible to reduce the entropy level of a single object by making that object colder. And you do that by taking thermal energy out of it. So if you have steam, you are able to reduce its temperature, turn it back into ice, and that ice has less entropy, it has less chaos than the steam did. So you can reduce something's entropy level. That's what the third law says. And the part about approaching absolute zero, what that is trying to say is that if you reduce something's temperature to absolute zero, then you will have removed all of its thermal energy and you will have removed all of its entropy. Since entropy is random movement, and since thermal energy creates random movement, the only way to completely get rid of entropy in an object is to remove all of its thermal energy and reduce its temperature to absolute zero. Absolute zero is the state of, the lowest temperature that exists, but it's also the lowest energy level that exists, and therefore it's also an entropy level of zero, because when you're at absolute zero, nothing is moving, and movement can't be chaotic if there's no movement at all. So, third law states, you can reduce a single object's entropy level by cooling that object down, and hypothetically, if you could cool that object to absolute zero, you would reduce its entropy level to absolute zero. Now, the problem with the third law is that in order to reduce, that object's thermal energy level, you had to take thermal energy out of it, and that thermal energy still exists. You didn't delete it. It has to go somewhere. So you can reduce one object's entropy level, but that energy and that entropy has to go somewhere else. It still exists. It's still part of the universe as a whole. You can't get rid of it. So the second law states that the entropy level of the entire universe is constantly increasing. The third law states that you can reduce a single object's entropy level, but that doesn't change the universe's entropy level. It's just single objects at a time. With that is a dive into all of the individual laws of thermodynamics. My plan for tomorrow is to look at some varied examples that tie in a bunch of different concepts that we've been talking about, tie in multiple laws of thermodynamics, tie in multiple concepts from chapters 10 and 11 to kind of show how it all fits together and to show some more examples of what might show up on your homework and on the upcoming test. So we're moving along through chapter 12. We'll be finishing chapter 12 soon. That does mean that test 1 is on the horizon. I would expect it in about a week or so. We will take time to prepare. We'll take class time to prepare, and you'll have time to study. I always give study materials for my tests, and we'll start looking at we'll look at examples tomorrow, and I'll start talking about some test information tomorrow. Are there any questions, comments, needs, concerns at this particular time? All right. If not, we'll break here like we usually do. Now, normally I stay in this call for an hour. I stay in this call until noon, usually, in case you jump back in with questions. Today, I won't be able to do that. I have something I have to attend to this particular morning. So, sorry about that. If you do have, we'll break here. You can go about your business. If you have any questions at all today about anything, be it, these concepts or homework, email me, let me know. I will answer emails all hours of the day. I'm rambling again. Well, we'll reconvene tomorrow, looking at examples and talking about the upcoming test. So if there's no questions or needs at this particular time, then I will see you guys tomorrow.